Last class we discussed about one of the functions of UDP, multiplexing and demultiplexing. Today we'll see the actual UDP segment structure. How does the UDP packet looks like? Now, one of the characteristics of UDP is that UDP is connectionless. That means that if an application uses UDP, what happens is the data comes from the application layer. The UDP takes the data, divides it into a small number of segments or packets, and immediately sends those packets to the network layer for onward transmission. If an application uses TCP instead of UDP, what happens is the data comes from the application layer, TCP divides it into a small number of packets, and before actually transmitting the actual data packets, TCP establishes some sort of connection. Connection means just if two normal human beings start speaking to each other and they greet before speaking, like saying hi, hello sort of things. TCP actually does that. Before sending the actual data, it establishes some sort of handshaking or connection. That's why TCP is called connection oriented. However, UDP does not do any such thing. It simply takes the data, divide into small number of packets, and blast the packets away to the network layer without any sort of handshaking with the other side. And that's why UDP is known as connectionless. There is no connection establishment, no handshaking, no hi hello sort of things while using UDP. Now, one thing be very clear, sometimes there are certain confusions. Many different literature, many different books use different nomenclature. Some books use the term packet, some books use the term segment, some books specifically use the term datagram for UDP. UDP is very popularly known as a UDP datagram. Now these terms are synonymous. The data comes from the application layer. UDP or TCP divided into small number of segments. Some books uh, term these segments as a packet. Some books term these small segments as segment. So whether someone refers to it as an UDP packet or UDP segment, they are synonymous. So don't confuse about it. UDP, very popular in some books, are also the UDP segments are known as UDP datagrams. Now, datagrams, this particular word is also used in the network layer. So sometimes there might be some confusion, but don't worry about it. Always understand that a UDP packet, a UDP segment, and UDP datagram is the same thing. To avoid any confusion, we'll generally use the word segment or packet. TCP, the same thing for TCP. The small segments of TCP are also known as either packets or segments. However, the word datagram is not used for TCP. Now, let's understand what are the advantages of UDP. We have seen in the first lecture that why any application would be interested to use UDP. We saw that because UDP is a faster protocol compared to TCP, that's why those applications for which time is an important factor would use UDP. Now, why would be UDP faster? Why is UDP faster? There are certain reasons why UDP is faster. First of all, there is no waiting. What does it mean? If an application uses TCP, what happens is TCP, there are certain situations in TCP where as soon as data arrives from the application layer, TCP has to wait for a certain amount of time depending on the traffic in the network. This is something we'll discuss in TCP. This is something known as congestion control. That means if data comes from the application, but there is a congestion in the network, TCP will not immediately send the data. It would do some sort of technique known as congestion control. We'll discuss about that. But UDP does not wait for any such thing. Data arrives from the application layer. As soon as the segment or packet is ready, the data is sent immediately without bothering about what is happening in the network or what is the status of the receiver at this current moment. So UDP does not wait. There is no waiting in UDP. As soon as data arrives from the application layer, the data is sent after making the segment. That's why there is no waiting in UDP. The second part no connection establishment, we have already seen. Because TCP does not do any sort of handshaking, it does not have to wait for some amount of time for initial connection establishment. This initial connection establishment or handshaking takes certain amount of time. Because UDP does not perform this handshaking, it does not have to wait for this phase. Now, the third step, no connection state has to be maintained. If you use TCP, because TCP is connection oriented, because it guarantees data, that's why it has to maintain some sort of buffers, some memory space to hold segments until and unless those segments are delivered to reordered segments, all sort of such things. Because no connection is established, that's why no connection states are maintained in UDP, and this ensures that UDP is lightweight. It does not take any amount of time for establishing these buffers or memory space. And finally, less header overhead. We see that both TCP and UDP insert some header information in the segments. We have already seen one of the header information, source port and destination port. Now, the number of header information in UDP is much less than the header information in TCP. This should be obvious because TCP performs a lot more tasks than UDP. That's why the number of headers in TCP would obviously be greater than the number of headers in UDP. In fact, TCP has 20 bytes of header information, whereas UDP only uses 8 bytes of header information. We'll see this header information right now. Because there is less amount of header in UDP, that's why the size of the UDP packet would obviously be smaller than a corresponding TCP packet, and because it's a smaller packet compared to TCP, obviously the delay in sending a smaller packet would be less than the delay in sending a corresponding bigger packet. So these are some of the advantages of UDP over TCP. Now, finally, we look at the most important part, the UDP segment structure. How does a UDP segment or a UDP packet looks like? So, data comes from the application layer. UDP divides it in smaller number of packets. Each of these UDP packets looks like this. So this is the UDP segment structure, the UDP packet structure. How does the UDP packet looks like? Every UDP packet would have these four: source port number, destination port number, length, and checksum. These four fields would be there in every UDP packet. These four fields are the header fields of UDP. The final part, the application data message, this part, this is the actual data that is being sent from the application layer. So say your application layer sends 20 bytes of data. Whatever application you are using, say it sends 20 bytes of data, and UDP divides into two smaller segments of 10 bytes of data each. These 10 bytes would come in this application data part. So there would be two segments like this. One segment contains 10 bytes of application data, the other segment also containing 10 bytes of application data. These four fields, source port number, destination port number, length, and checksum, these four fields would be there in both these segments. These are the header informations. If you look at it, the source port number is of 16 bits, the destination port number is of 16 bits. This we have discussed in lecture 2. The length field, we'll discuss what the length field is, and the checksum field, they are also 16 bits each. That means 2 bytes for source port number, 2 bytes for destination port number, 2 bytes for this length field, and 2 bytes for the checksum. That makes 8 bytes. 8 bytes of header information would always be there in a UDP segment apart from the application data. So we have a fixed size of 8 bytes of UDP header that would be contained in every UDP segment. Now let's discuss each of these header fields in details, these four header fields. Now source port and destination port, this we have already discussed in lecture 2. So if you have not gone through the lecture 2, I advise you to go through the lecture 2 to understand what source port and destination port number is. Briefly, source port and destination port is used for multiplexing and demultiplexing. These are indicated by using 16 bits. So source port and destination port, they both use 16 bits. Now the third header field, length, This is a field that specifies the size of the UDP segment. The size of the UDP segment uh, basic covers both the data part and the header part. For example, if the application data part 10 bytes of data, the header part is 8 bytes, that means the size of the UDP segment is 18 bytes. So the length field will contain the binary value of 8. Be very clear about it again. The data comes from the application layer, say 20 bytes came from the application layer. And UDP creates only one segment and the application data part contains 20 bytes of application layer data. The header size is 8 bytes. 8 bytes is fixed. Every UDP segment's header size is 8 bytes. So 20 bytes of application layer data, 8 bytes of header field, that makes the total segment size of 28 bytes. So this length field will contain the value indicating that this UDP segment size is of 28 bytes. So length, a 16-bit field, specifies the number of bytes in the segment, whatever the segment size is, both the data part as well as the header part. And the final 16 bits checksum, this is used for error detection. This we'll discuss in the next lecture how checksum is calculated. So these are 4 header fields: source port, destination port. These 2 are used for multiplexing and demultiplexing. Length is used to indicate the size of the UDP segment, and checksum is used for error detection. This we will discuss in the subsequent lecture. Now you may be wondering, why do you want to specify the length of a UDP segment? Now remember, the data flows from the sender to the receiver one by one. First segment, second segment, third segment. How does the receiver know where the first segment ends, where the second segment starts? And that's because the segment size may not be equal. It is not necessary that every segment size would be equal. So one segment may be of 20 bytes, another segment may be of 30 bytes, another may be of 40 bytes. So the receiver has to understand where the first segment ends, where the next segment begins. To ensure that the receiver understands the segregation between the segments, this length of the segment is specified in the length part. This clearly specifies that this segment starts at this number of bytes and ends at this number of bytes. If it specifies 28 bytes, that means starting from 0th byte to 27th byte, this is segment 1. Next, the subsequent segment becomes. So these 4 header fields are always used in the UDP segment. Now, the application, these size of the segments are always in multiple of bytes. Let me clarify this once again. The size of a UDP segment, the total size of a UDP segment needs to be in multiple of 2 bytes. That means the size of a UDP segment can be 10 bytes, can be 12 bytes, can be 14 bytes, can be 16 bytes, but it cannot be something like 11 bytes or 13 bytes or 15 bytes. So what happens if the data comes from application layer which is of not multiples of 2 bytes? Let's say I have 33 bits of data coming from application layer. That does not make multiple of 2 bytes. So when I have data which are not multiple of 2 bytes, then I have to pad extra zeros to make it of size of multiples of 2 bytes. So I have data coming from the application layer. I make a UDP segment. 8 bytes are fixed for header information, and then the data part should be multiple of 2 bytes. So if you look at this diagram, so I have some data which finishes at this point. So I have to make it multiple of 2 bytes. So this part I have to pad, or I have to insert extra zeros. This is known as zero padding. So this happens when the size of data is coming from the application layer does not make it a multiple of 2 bytes. So this is known as padding of zeros, extra padding of zeros in UDP segments. So after discussing this UDP segment structure, what can be the maximum size of a UDP segment? Can you think about it? What can be the maximum size of a UDP segment? Irrespective of the data coming from the application. Let's say I have a huge amount of data coming from the application layer. Uh, can I insert all the data into one UDP segment? What would be the size, maximum size of a UDP segment? Which field would give you this answer? Think for a moment. You must have seen the field which indicates the size of the UDP segment, both data plus header part. And this field was length. If you remember the segment structure, let's come back to the segment structure. So this UDP length indicates the size of the whole data packet. Now this size of this field is 16 bits. The size of the header field that indicates the size of the UDP segment is of 16 bits, which essentially means that a maximum size of 2 to the power 16 can be indicated to be the maximum size of a UDP segment. This makes a UDP segment of maximum size of 6553 bytes. Now, because 8 bytes are header information, that leaves 65527 bytes of data. This is the maximum amount of data that can be inserted inside a UDP segment. So essentially, it means that the maximum size of a UDP segment can be of 6553 bytes. But in reality, in real networking, no UDP segment can be of this size. In fact, the size of a UDP segment is much smaller than this maximum size that can be theoretically possible. This is theoretically possible, but practically a UDP segment size is never of this huge size. Normally they are much smaller size. Now why? Because there are underlying constraints. There are several constraints placed by different aspects. For example, the underlying layer, network layer creates its own header. When we discuss network layer, we'll see that the data coming from the transport layer, either from TCP or UDP, when sent to the network layer would insert its own header information. So there are certain constraints placed by network layer. Then that packet is subsequently sent to the data link layer. Data link layer again adds its own information, own header information. So these different constraints placed by lower layers place some sort of limitations to the size of the packet that can be created by UDP or TCP. Another constraint is placed by your operating system. Your operating system has its own constraints depending on its buffer size, depending on different aspects of operating system. The size of the segments of the UDP segment is constrained by this aspect of operating systems. And finally, the data is actually transmitted finally from the data link layer and the physical layer. They are the actual layers which is responsible for sending the data from one node to another node. Now these limitations place the maximum restrictions of the data, the size of the UDP segment. As an example, if I use Ethernet in data link layer, there are different data link layer technologies. If I use Ethernet, which is for LAN, Ethernet has a limitation. That limitation is known as maximum transfer unit. This maximum transfer unit indicates that the maximum unit size of a segment that can be sent over Ethernet. Ethernet is a data link layer technology. So if my data link layer technology uses Ethernet, Internet says that the maximum size of a segment can be only of 1500 bytes. That means the segment created by UDP that goes to the network layer inserts its own header size, then it goes to the data link layer inserts its own header size. The final segment that is transmitted, that can be transmitted over Ethernet, the maximum size can be of 1500 bytes only. That means the segment created in UDP has to be even less than this 1500 bytes. Why less than 1500 bytes? Because some bytes of header information is indicated in that is added in the network layer. Some more header information is added in the data link layer. The total size has to be less than 1500 bytes if I use Ethernet. Some other technologies would have even much lesser size. So if I use Ethernet, that means my UDP segment, the size of my UDP segment has to be less than this 1500 bytes. So though theoretically it is possible that the maximum size of a UDP segment can be of 6553 bytes, but in practical reality, the size of a UDP segment is much less, and this constraint is because of the constraint placed by the underlying layers. Most importantly, the maximum transfer unit of data link layer. Maximum transfer unit indicates the maximum size of the unit that can be delivered, that can be handled by the data link layer of that particular network on which we are sending data. So I hope this aspect is clear. So today we have discussed about the structure, the segment structure of UDP. We have already discussed the first two header fields, source port and destination port number, in lecture 2. We discuss about the length field today. Subsequent class will discuss about the final field, checksum. Checksum is used for error detection. We'll see the actual method how this checksum is calculated in the subsequent lecture. Thank you.